Good morning, Shandip. I'm good. How are you?
Yeah, going well.
Yeah, so I'm done with my semester finally. So, I thought I should start attending the meetings
Right,
again.
right, right. Yeah, our semester has also wrapped up last week.
Right, yeah.
Okay. Uh, Sorgo, let us start then.
Yeah, Anirbandha will start the initial part.
Oh, fine.
So good morning. Uh, in this presentation, me and Argha will introduce some basic ideas about mmWave sensing and would try to motivate why mmWave sensing has grown popularity in the various research domains. So to start with, I will introduce some literature ideas like where the mmWave sensing has been used and uh, in what are the basic problems that has been addressed by mmWave sensing. And afterwards, Argo will continue with the core functionality of mmWave sensing and will introduce one of the papers. So when we consider the sensing in the frequency domain, we have some basic ideas that the various waves they get scattered or reflected by different objects on its path of propagation, and this reflected waves, when received by the receiver antenna, and can be processed to extract different information such as the position, movement, direction, and speed of various bodies that the wave has encountered throughout this path. So, in case of uh, in the literature, we can see that various frequency waves such as Bluetooth, acoustics, radio frequencies has been used for this purpose to address various problems. The basic idea is the transmitter and receiver communicate with some signals. The feature is extracted on the receiver side from the received signal, and based on those collected information, some processing is performed to infer something. Uh, in literature, basically, these are the frequencies which has been used for sensing purpose. Each of them has some key characteristics which has motivated its use. For instance, LoRa has a very long range, and because of this, LoRa can be used or has been used to sense breathing and heart rate monitoring in a very long distance. Wi-Fi has pervasiveness as compared to the others, and that's why we can see a large number of works which has used Wi-Fi based sensing, which basically extracts the channel state information from the Wi-Fi signal and then performs a set of processing on it to extract this information. These are some of the problems which has been addressed by different types of frequency waves, and as we are aware that the frequency which, for instance, the millimeter wave frequency is much higher than the frequency used in case of Wi-Fi. It can be seen that there are certain very certain tasks which are of low motion, minimal motion, which are addressed by millimeter wave, the such as the heartbeat monitoring as well as uh, Wi-Fi. The reason behind this will be introduced by Orko after a few slides. Similarly, we can see that Bluetooth has very less amount of applications in the literature, whereas LoRa has long-range estimations of breathing monitoring, heart rate monitoring, etc. Moving towards millimeter wave sensing, it has been used to address a large number of problems such as position tracking, various activity recognition, and very even voice recognition, and as such. The frequencies which has been used by millimeter wave sensors are this. However, if we see that the earlier works tried to focus on the frequency range of 60 gigahertz to 69 gigahertz because of the popularity of this frequency range. However, the recent works primarily focuses on the frequency band of 77 to 81 gigahertz uh, because of the large number of commercially available devices that uses this particular frequency range. The modulation techniques that we see, which were used by different types of mmWave radars, are this, like phase modulation, continuous wave modulation, and frequency modulated continuous wave. However, the most of the commercially used devices have used frequency modulated continuous wave, and this is the one which is the highest popularity uh, in case of various applications. While collecting the information from while using this type of radar, there are number of information has been collected. For instance, the range, the radial velocity, and the angle of arrival computed on the azimuthal angle and angle of elevation. Then Doppler shift, the point clouds. These are the information which primarily were collected in different works and were processed afterwards to infer certain things. If we look into the types of models that has been used for various inference, we have the phase tracking, which tries to calculate various two-dimensional positions in a Cartesian coordinates. Similarly, singular value decomposition tries to extract singular vectors from collected spectrogram of different frequency bands. Then we have the angle time model, which tries to calculate the position of the object based on the multipath component time of flight and the angle of arrival information. There are other machine learning models which are also used in case of various works, such as SVM and neural networks. So since they are very general ideas, so I didn't just put any extra information on this. Then there are triangulation models which are used to estimate the position of the objects. And these are some of the models. Other than that, there are also pre-processing techniques such as first Fourier transformations, two-level first Fourier transformations, which are used in many of the works to calculate the velocity and position of the objects. From here onwards, Argo will introduce the core idea of FMCW radars, which I have said as one of the most popular radars, and then he will introduce one of the papers. So, Argo.
Yeah. So you can stop sharing your screen. Okay. So okay. From here onwards, I will discuss how these FMCW radars or frequency modulated continuous wave radars they actually work. We need to understand the actual working of these FMCW radars so that finally we can figure out what are the different derivations that we have, like what are the range resolutions, what is how the actual range is calculated, so that like we can compare these equations from different multimodal perspective. Okay, so the broad idea is that we have a radar, and in front of that radar we have certain object present. So how this radar is able to capture or able to estimate the range of this object, and like what if I have multiple objects in front of the radar, how the corresponding distance or angle of arrival is computed, or like what if I have these two objects very close to each other, and how my radar is able to resolve these two objects as different objects, and what is the maximum distance, how far my FMCW radar can capture. So for that I need to understand how actually this FMCW radar works. So FMCW radars, they basically transmit a chirp. So this chirp is basically a sinusoid whose frequency varies over time. So initially we can see from this graph that initially the frequency is very low, but gradually over time this frequency increases. So if I plot the frequency versus time for this particular sinusoid, I can see that the frequency is gradually increasing over time. So suppose the carrier frequency of this signal is 77 gigahertz, and I have a bandwidth of 4 gigahertz. Then from 77 it will gradually increase up to 81 gigahertz, and this is the time window for which I am sending this chart, and this is the slope, and the slope is important because the slope basically represents the chirp rate. Okay, if I have a higher slope, then the chirp is I will call it as a faster chirp. If I have a low slope, then I will call it as a slower chirp. Okay, so these are the components that FMCW radar consists of. So I have a synthesizer that basically generates this chirp, and using its transmission antenna, it basically transmits that chirp. And like suppose I have some object in front of the radar, then once the transmitted chirp gets reflected back by that object, the RX antenna captures that chirp, and here I have a mixer. So this mixture basically takes the transmission chirp and the received chirp as its input, and it generates intermediate frequency or the IF signal. So mathematically this transmission chirp can be given as sin omega 1t plus phi 1, and the received signal can be given as like this. So this IF signal or the output of the mixture can be given as this equation. Okay. So here you can see that this omega 1 or omega 2, this frequency lie within the range of 77 or 81. So that's a very high frequency, but the IF signal is basically a difference between these two, right? So that makes it a low frequency signal, not very high like 77 gigahertz, but it becomes the frequency becomes around 4 gigahertz for the IF signal. So it is a low frequency signal, and also it has certain phase difference based on the transmitted chirp and the received chirp, phi 1 minus phi 2. So basically once I generate this IF signal from the mixture, now the signal processing starts on top of this IF signal to infer some informations like where the object is located, what is the angle of arrival, what is the range resolutions, all that thing. So here you can see if I plot the frequency over time for the transmission chart. So this is the slope representing the transmission chart, and after a time gap of tau. So tau basically represents the round trip time. Okay, once the object is once there is some object and the transmitted chart gets reflected back from that object, I will start receiving the RX chart. And so here I have so here I have these two charts, transmission chart and receive chart, and within this time window both these charts lies. So in this particular time frame our mixer can generate the IF signal, right. So so the IF signal is basically having this frequency. So the frequency of the transmitter chart minus the frequency of the receive chart. So so what is the actual value of this frequency? From this triangle I can see my S is basically equals to this height divided by tau. So this height basically is S tau, right, and tau is the round trip time. So if the object is located at a distance of d, then the total round trip time will become 2d by c, right. So where c is the speed of light. So from there I can figure out the actual frequency tone of this IF signal. So the frequency tone of this IF signal is basically S2d by c, right. So yeah, so our radar basically captures this IF signal, and from the IF signal's frequency or frequency spectrum I can easily calculate the distance where the object is located. And if I have multiple objects in front of the radar, then I will have multiple RX charts, right. And based on these multiple RX charts I will have multiple frequency tone of the IF signal, and accordingly from these frequency tones I can calculate like using this formula S2d by c, I can calculate where the actual object is located. So Fourier transform is at the core of this FMCW radars. So once I have this IF signal in time domain, I can apply Fourier transform on top of that to generate this IF frequency spectrum. So so basically this Fourier transform gives you the frequency where you have very high magnitude, right, where the actual object is located, and you will have a peak in that particular frequency. So so you can see here like the smaller so the frequency has a direct relation with the distance. So smaller the frequency, the object is much more closer, right, and higher the frequency, the object is much beyond that, much more distance from the radar. So so yes, so this plot is also known as range FFT plot, because it gives you a broad idea where the object is located, right. So so yes, we can figure out where the object is located. Now our next task is to figure out what is the range resolution. Suppose I have two objects that are very close to each other. In that case, the two received chart will lie very close to each other, and if I see the time domain IF signal plot, since they are very close, once I apply Fourier transform on top of this time domain IF signal, I will have a single peak in the frequency domain, right. So that makes it very difficult to distinguish two objects which are very close. But what if I increase this observation window? If I increase the observation window, so as I can see here, the two time domain plots can be easily distinguished, and corresponding frequency domain or corresponding Fourier transform can easily distinguish these two these two objects, right. So the thing is, if I increase the time window, then also my bandwidth increases, right. So so intuitively, greater the bandwidth, the better is the resolution. So now I'll try to derive the actual range resolution of this FMCW radars. So as we have discussed earlier, the IF tone frequency is equals to the S2d by c, right, where the frequency is directly proportional to the distance. And if I have like two objects that are very close to each other, then the difference between the two IF tones, or delta f, that will become equal to S2 delta d by c, right. So delta d is basically the small distance between the two objects, and delta f is the difference between the two IF frequency charts. And so mathematically, this delta f should be greater than the time window, 1 by the time window. For the time window is this one, right? So from these two equations, I can once I do some derivations, I can figure out this delta d, or the smallest distance that my FMCW radar can support. So this delta d is equals to c by 2b, where b is the bandwidth and c is the speed of light. So speed of light is constant, but the bandwidth we can vary. So from this equation we can say that the range resolution depends only on the bandwidth swept by the charge, right? So here, so this equation is important if we look it from multimodal perspective, such as Wi-Fi. Wi-Fi provides you a bandwidth of I think 5 megahertz to 22 megahertz, and in some cases 40 megahertz. So for 40 megahertz, if you use FMCW radar based concept, then Wi-Fi can support 3.75 meter range resolution. And if you use ultra wideband radar, so ultra wideband radar has usually 500 megahertz bandwidth. In that case, it can support 30 centimeter range resolutions. But for millimeter wave, we have a bandwidth of 4 gigahertz, right? So for this 4 gigahertz, or for this huge bandwidth, I can capture a range resolution of 3.75 centimeter. So that makes millimeter wave sensing very important. And this point is important because we have some it's not because that millimeter wave frequencies have a lower wavelength in the range of millimeter wave, that is why we are able to capture very small scale movements, but it is because of this huge bandwidth that mmWave supports, and because of that we are able to have a better range resolution. Okay, and another important point is like if you use FMCW based acoustic radar or acoustic receiver in transceiver, in that case the speed of acoustic signal is very low, right, in comparison to speed of light, and that makes acoustic signal also important, because the range resolution becomes very low in that case, right. So so we are able to figure out the range where the object is located and the range resolutions. So what if I have two objects in front of the radar which are equidistant to each other? In that case, your IF tone, or the frequency, which is equals to S2D by C. So since the distance is equal, you will have a single frequency magnitude, or single peak in the frequency domain if you apply Fourier transform. So in that case, how we are going to figure out this two, like how we are going to distinguish these two objects which are equidistant? So now we need to understand the phase of this IF signal. So phase is basically if you have a time domain signal, if you apply Fourier transform on top of that, you will have two different information. One is the frequency domain spectrum, which gives you like for a particular frequency magnitude you will have a peak, and another information is the phase. Okay. So so it is basically a complex number. The Fourier transform is basically a complex number. It gives you magnitude and phase, and where phase is basically the starting point of this time domain signal. So here you can see that the IF signal started at starting from 0 amplitude, right? But for this case the amplitude is 1. So they are the phase difference between these two signals is 90 degree, and accordingly the phasor will give you corresponding phase differences. So so these are the phase of the IF signal. Now based on this information we are going to see like what are the other informations that we can capture. So here I have this transmission chart, and like after a round trip time I have the RX chart, and so this is the mixer output, or the intermediate frequency signal. And what if this object starts moving, if this object starts moving for a time say delta tau, okay, so for that particular movement I will receive this Rx chart after some time, right, that delta tau, and based on that I will have corresponding phase difference between these two signals, between these 2 points A and D or C and F, right. So this phase gap between the two received signal is important, because here from this equation you can see the phase difference is equals to 2 pi fc delta tau. Delta tau is the time after which the second received signal is there. So from this delta tau is basically the also the distance covered by that object, right. So so from this equation I can see that if I have some idea about the phase gap between the two signals, two IF signals, then easily I can calculate the distance traversed by the signal, by the distance traversed by the object, right. So what if I send two charts? The first chart is sent initially, and after a time say Tc, I am sending another chart. So accordingly, after this time Tc, once I receive the RF signal, the IF signal will have a phase shift, right, and from this phase shift I can calculate the distance traversed by that object, and this distance is equals to the velocity of that object and the time taken in between, the Tc. So from this V and Tc, like the Tc is known to me and the phase difference is also known. So from here I can calculate the velocity at which my object is moving, right. So so yes, we are able to capture the range, we are able to capture the range resolution, and also we are able to capture how the object is moving, like what is the small scale movement of that object and what is the velocity of that object. So so here you can see FMCW radar, they basically have a frame. In that frame they send multiple charts, okay. So if you apply range FFT on top of the first IF signal, you will have this frequency spectrum, right. You will easily calculate, you will be able to easily calculate the range profiles, and then you have in a single frame you are sending multiple charts. Say you are sending n charts. So for this n charts, if I start filling the corresponding phase difference, then then where the object is located in those range profiles, I will have corresponding phase differences, right, corresponding movement of the object. So this plot is important, because this plot gives you the idea where the object is located and what is the velocity in which the object is moving. Yeah, so in literature they have used different name for the same plot, like here they have used first time versus slow time. Somewhere you will see it is range versus Doppler, or range versus velocity plot. Okay, they are the same plots basically. Or somewhere they have named it as a 2D FFT plot, because here we have 1D FFT at the range domain and second FFT at the phase domain. So so they have named it as a 2D FFT plot. Yeah. So the next task is to figure out the angle of arrival of the object. So suppose I have a single transmission antenna and I have two RX antennas. So if the object is located somewhere here, then the RX antenna which is closer to that object will the chart will cover a distance of d for the RX antenna which is closer, but for this RX antenna it will traverse a delta d more distance, right. So if I take these two received signal parallel to each other, then suppose the object is present at an angle theta. So for this angle theta, the second chart will traverse d sin theta extra distance, right. So earlier I have showed like I have phase difference between these two received signals, right. So from this phase difference, the phase difference can be given as 2 pi the delta d by lambda, right, the earlier equation. So delta d is here the d sin theta. So from this equation I can calculate theta, or the angle of arrival of that object, right. So yeah, I know the phase difference, I know other parameters, so I can easily calculate the I can easily calculate the angle of arrival. So so now imagine it in 3D. So these two RX antenna are kept horizontally, right. So in that case this theta basically is the azimuthal angle, but if you keep these two RX antenna vertically, then the theta will be basically your elevation angle, right. So you will have two different information, one is the azimuthal angle of arrival and the other one is the elevation angle of arrival. From these two angles you will be able to figure out where the actual object is located, or the angle of arrival. So now the earlier problem is resolved. Like if I have two objects which are equidistant to each other, in that case they will have different angle of arrivals, and from that information I will be able to easily distinguish these two objects. Okay, so yeah, so that's the theoretical part of this FMCW radar. If you have any question, then you can ask. Okay, so now I will discuss some of the recent works in literature on this FMCW radars. So FMCW radars, mostly the mmWave FMCW radars are used for human sensing. Human sensing for vital sign monitoring, such as heart rate waveform generation or breathing rate waveform generations. So this paper got published in Infocom 2022, where they have used the FMCW mmWave radar to retrieve heart rate waveform for a driver in driving environments. So the major challenge in this paper is that not only the driver is moving, but not only the driver is having certain motion, but the entire setup is also moving, right. So that will add up more noise in the waveform, and that will make it more difficult to generate the corresponding vital signs. So that's the major challenge addressed in this paper. And another paper published in Infocom 22, where they have like retrieved this heartbeat waveform using multimodal RF sensing. They have used Wi-Fi, mmWave and ultra wideband radars, and have shown that yes, mmWave radar is much more better in comparison to Wi-Fi in retrieving the heart rate waveforms. And another paper got published in MovieCom 2021, where like they have generated the vital signs. So vital signs are basically the heart rate and the breathing rate waveforms. So these waveforms are generated when the user is moving, user is having certain motion. So that also makes the problem challenging. And another paper got published in MovieSys 2022, where they have used the FMCW mmWave radar to retrieve entire 3D model of a particular user. So these are the works done in human sensing, and some recent works are also done in sound regeneration. So you have certain sound source. Because of that sound source, maybe it can be a speaker or it can be our human vocal fold. Okay, so the human vocal fold or the speaker, they have certain vibrations to generate the sound, right? So the task of this millimeter wave FMCW radar is to capture these vibrations. Once these vibrations are captured, from that vibration spectrum, vibration waveform, how can we generate the actual acoustic signal? So that's the challenge they have addressed in this sound regeneration domain. So in Infocom 22, here we have two papers where they have addressed the same challenge. One is where they have used a speaker, and based on the speaker's vibration, they try to generate the actual acoustic signal. And for another signal, another paper, here like they have used another layer between your sensing device and between your sound source. They have used this piezoelectric device. So you have that sound source. From that sound source, it is coming at the piezoelectric device. The piezoelectric device is having certain vibrations, and our mmWave sensor is capturing that vibrations. So here authors basically motivated that the vibrations in the piezoelectric effect gives you a better a better resolution in capturing the acoustic signal. And this paper I have already presented. So it was from Census 2021. The paper is titled Wave Voice, where they have basically fused acoustic signal as well as the mmWave signal to retrieve the speech of a human. So here your sound source is basically the human vocal cord. So based on the vibrations, mmWave signal, mmWave sensor try to capture the acoustic signal. Right, and some papers have done some problems are on localization, where using the FMCW mmWave radar, they tried to capture where the actual user or where the actual object is present. Okay. So now I will give you a broad idea what is happening in this paper, Movify, which was published in Movicom 21. So in this paper, the broad idea is to capture heart rate waveform from FMCW mmWave radar. So for this for capturing heart rate waveform, we have different modalities. We can have contact sensing, where using some wearable sensors we can capture the heart rate waveforms. But contact sensing is like sometimes it is uncomfortable from user's perspective. What if a user is sleeping and we are giving him these wearables to capture so that makes it difficult for the user when he is sleeping, right. So that makes it uncomfortable. But this RF sensing or contactless sensing, that is much more much more better from the user's comfort zone. So for this contact free sensing, we have light or acoustic signals, or we can have the RF signals. For light and acoustic, these signals can get easily affected by the background. So if like based on the light condition of the room, my light signals can get easily affected, or based on the acoustic noise present in that room, our acoustic signal can also get affected, right. So these are the drawbacks that we have for light or acoustic based contact free sensing. But if I use RF based sensing such as Wi-Fi or mmWave, in that case we don't have those background effects, and mmWave signals gives you a very good range resolutions, so that you can capture small scale chest movement because of breathing or because of heartbeats. So so as we have discussed earlier, using this FMCW radar, we can generate the range profile where the object is present, and in that particular range profile, based on multiple charts, I have various phase differences, and based on these phase differences, or based on this phase differences, I can capture the small scale movement of this particular range profile of this particular object, right. So here they have shown two different scenarios. One where the user is sitting statically in front of the FMCW radar. In that case, from the RF waveform, we can capture we can recover the heart rate waveform easily. So so basically the breathing rate or heart rate, they have certain amplitudes, and based on these amplitudes we have certain frequencies on which the breathing or heart rate actually works. So if I apply some band pass filter on top of this received IF signal, I can easily generate the heart rate waveforms. So this part is done in literature, it is already done. So once you have the RF signal, you can easily capture the heart rate waveform based on this band pass filters. But when the user starts moving, in the here the user is walking in a treadmill. In that case, retrieving the heart rate waveform from the raw RF signal, that becomes difficult. So this problem is addressed in this paper. So here they have shown different mobility condition of the user. So in this plot, here the user is basically playing with his phone. Here he is walking on a treadmill. Here is having circular motion, standing up and sitting down, and here the user is sitting statically. So in all these 4 cases, if I see the signal matrix, the slow time signal or the slow time domain signal, it has a particular waveform, right? So if I have certain circular motions, in that case the slow time motions will be different, but for sitting statically, in that case this is the corresponding slow time variations. So here authors have motivated that based on these different activities, our task is to capture this temporal variations in the slow time waveform. Okay, so this slow time waveform is plotted here, and here authors tried to capture this temporal variations. So for this sitting up and sitting down, it will have a periodic motions, or walking in a treadmill, walking on a treadmill, it will have certain periodic motions. So using this encoder decoder network, here they tried to capture this small scale periodic movement of that user. So once that movement is captured, if I remove that movement from my raw slow time waveform, then I will be able to capture a better signal, and from that signal, if I apply some filter for breathing and heart rates, then I will be able to retrieve the corresponding waveforms. So so in this paper they have done that. So in motion robust where the user is moving, in that cases authors are able to capture the heart rate and breathing waveform. Yeah. So based on these recent works, we are thinking to implement some, like we are trying to figure out where we can apply like certain new advancement in mmWave sensing. So so here we thought of this plan. So suppose we have a user, and in front of that user I have some obstacle present, and here is the sensor device. Here like mmWave can't move, like mmWave doesn't have penetrability, right? Wi-Fi have, like Wi-Fi can easily penetrate through some obstacle, but mmWave can't. So our task is to add multimodal sensing here. So instead of mmWave, I will use Wi-Fi. Our Wi-Fi will be able to penetrate through this obstacle and will be able to capture the actual location of the user. And mmWave, it will have certain multipath motions, multipath reflections, and from that reflection the user's location is captured by the mmWave sensor. So based on these two modalities, mmWave and Wi-Fi, if I apply some correlation on top of the two data, I will be able to figure out like if I have certain correlation between the two modalities, then I can say that yes, the user is present or not, right? So so our task is basically to use this Wi-Fi modality, because Wi-Fi has a better penetrability, Wi-Fi has a better coverage area. We are going to use that that modality or that help from Wi-Fi, and we are going to use that so to capture the actual location of the user. And once the user's presence is detected, now I will use the mmWave modality to understand the better small scale movement happening at the user end, right? So that's the idea that we are thinking of. So so basically we are trying to figure out the vital sign monitoring of a human in non-line of sight scenarios where mmWave fails but Wi-Fi can capture. And so this is one perspective. Another perspective can be, suppose the user is present somewhere here, okay, and this is the range or this is the field of view where your mmWave sensor works, right? So in that case, naturally the mmWave sensor can't capture the actual location of that user, right? But mmWave have this multipath propagation. So suppose I have two different walls located somewhere like this. So based on the multipath reflections, finally our user is the actual user's location is retrieved by the mmWave sensor, but the range profile of that user will be very long, right? So the range will have a very wrong value if you check it. But if you have Wi-Fi, then Wi-Fi has a better coverage or better field of view. So Wi-Fi can easily capture the actual user's location, right? So using this Wi-Fi modality, we can capture the user's location, and once I have the actual user's location, then using the mmWave modality, I can start implementing the vital sign monitoring part. Okay, so that's it.
So, Orgo means, have you been able to thought of any particular application where this non-line of sight can be useful? I think that we were discussing earlier.
Yes, so right, we need to find out the actual application where this entire system fits. So right now we are not able to figure out the actual applications, but like I thought, as I said, like this obstacle can be a human, like I have multiple humans. In that case, based on this system design, I will be able to figure out the actual user's location, and I can apply vital sign monitoring in multi-users scenario.
Okay.
So I I have one question. Actually, a couple. Maybe I'll think and I'll like ask you a few more later on. But just now I have one question, that how are you? Because you have Wi-Fi on one hand,
Hmm.
and then you have your mmWave in other hand.
Right.
So you are saying that you will have a cross-modal Doppler correlation, right?
Right.
So have you tried and tested this? Like, because although like these two signals are like in physical layer, they will be pretty different, and they are like, how should I say, like, and after their characteristics will be a lot difficult, well, like or a lot different. So do you think that finding their correlation, Doppler correlation, will be very easy, or won't be that difficult?
Yes, right. So I was also thinking about this, because the Doppler variations, like FMCW radar will give you a very good Doppler FFT,
That is fine.
but Wi-Fi, in Wi-Fi most of the literature they have used CSI based matrix, right? So I was thinking that let's see how this Doppler matrix and the CSI matrix, like, is there any correlation between these two?
Then there is a point, Orgo, because the Doppler matrix that you are talking about, it is mostly like it is like you are trying to obtain the velocity versus distance graph that we
Exactly.
used to have in class 10, 9, 10 or 11, 12, I don't know in which class. But it is like that, and it is analogous to that. And your CSI matrix is actually the almost exact representation of your channel state.
Right.
These are two different things. If you are trying to take correlations out of it, I don't know how that would work. And moreover, both of these will be like, if you want, because CSI is a matrix. Whenever you are
There are existing works to capture
Doppler in Wi-Fi.
Yes, sir.
in Wi-Fi. Okay, then that is fine.
So from CSI, so the steps can be like, from the CSI matrix, extract the Doppler information, and then compare the Doppler information between them.
Then that is fine. That's my primary question. I don't have any
Yeah.
idea. So if that is available and that can be obtained quickly, because otherwise these two are two separate things. From CSI, if you can find out a similar metric, then that is fine.
Like in this
So
paper Infocom 22, here they have used this multimodal RF sensing. They have used ultra wideband radar, Wi-Fi and mmWave, and here they have shown that yes, we can have this Doppler distance metric for Wi-Fi and for ultra wideband radar also. So I think
and
that
my
is possible.
following question would be that again, if there are works, you better let me know in that case. That is that if you are considering multipaths for mmWave, then once you receive those mmWave signals, like after all those multipath reflections, do you think that you
Yeah,
will like they won't be dumped, or
yes, yes,
they
there
they
will be
like
attenuation,
dampened enough?
very
There will
high
be a huge
attenuation, right?
yes.
So I
But
just need to see like how far actually I can I'll be able to capture the actual user. So yes, there will be attenuation, right? But it will
because
be up to
most of the
certain range.
mmWave applications that I have seen, they usually like FMCW chart based applications that I have seen, they usually keep the device a bit close to the subject.
Yeah.
So probably in the last Parcom paper or some census paper, I also saw that the FMCW sensor was actually moved accordingly in the environment, so that it is always in line of sight of the subject. I don't remember the exact venue, but there is one paper related to this. Anyway, so you may have to see how much that signal is attenuated if there are like there is a huge number of multipath.
Right.
Right, I'll just add in a little bit. I love the presentation, by the way, like very detailed, very nicely presented. I guess you might all have thought about this, but I was thinking about an application there where, based on what you were just talking out here. So one of the places that I could have thought about was in disaster management, basically a building collapse or something, where you could use the Wi-Fi to identify if a person is there and then see if they are still like how their vital signs are. I don't know if it'll work out or not, but yeah, so that is one of the applications that I was like that was going in my mind when you're talking about this.
Right.
Yeah. So Orko Bishak has written something in the chat.
Okay. Uh, Finding the correlation for some distant marker event between direct and reflected signals will be a better starting point. I think that will give clarity at all cross modality is required. Yes, right. So I think what Visakda wanted to say. See, this multipath is basically like we can have multiple multipaths also. So if I apply correlation on top of the same signal, then I think we'll be able to figure out actually there is a multipath or not. So that is also a good feedback. So I think.
Okay. Any other query or any other suggestion? Okay. If not, thanks, Orko. So the presentation was really nice and very detailed.
Yeah.
That's a kind of reward. Thanks. Okay. Thanks everyone for attending. So we'll be meeting next week. Take care. Bye for today.